All right, today we're diving into some really cool new science that could change how we heal broken bones. The paper has got a bit of a mouthful for a title. It's Polycaprolactone / F18 Bioactive glass scaffolds obtained via fused filament fabrication. But don't worry, the idea behind it is actually super simple and honestly pretty powerful. We're talking about using 3D printed materials to help our bodies rebuild themselves.
So first off, why is this even important? Well, here's the thing. Our world is getting older. By 2050, it's estimated that 1 in 6 people on the planet will be over 65. And with age, unfortunately, comes a higher risk of things like osteoporosis, which means more broken bones that are way harder to heal. This is a huge, growing medical challenge.
So the challenge is pretty clear, right? We need to do more than just slap a cast on a fracture and wait. The real question scientists are asking is, how can we actively help the body rebuild bone, making it faster and stronger than ever before?
And that brings us to this deep dive. We're looking at a brand new 2025 paper from the journal ACS Applied Polymer Materials. It comes from a team of researchers at the Federal University of San Carlos, and they think they have a pretty innovative solution.
And what is that solution? Well, it's basically a 3D printed helper. But they're not just printing some solid implant. No, they are building a really sophisticated scaffold, one that's designed to encourage new bone to grow right where you need it most.
The best way to think about it is exactly like the scaffolding you see on a building that's under construction. It's the same idea. These 3D printed structures are porous, creating this framework inside the body that gives new bone cells a place to grab onto, to grow, and to form brand new tissue.
Okay, so what are these things actually made of? The researchers tested a couple of different materials. The base is this biodegradable polymer called PCl. Think of it like a dissolving stitch that just harmlessly fades away over time. Then they made a special version by mixing that PCl with something called F18 bioactive glass. This stuff is designed to release ions that basically give our cells a little kickstart.
All right, so we've got this new composite material. But the first, most obvious question is it strong enough? Can it actually support the body while it's healing? It's time for the strength test.
And this is where we hit our first big surprise. I mean, you'd think adding glass would make the material stronger, right? Well, nope. The exact opposite happened. If you look at this graph, the materials with the bioactive glass, that's the green lines, were actually weaker. They just couldn't handle as much stress as the pure polymer. So what gives? Well, a quick look under the microscope tells the whole story. See those little yellow arrows? They're pointing to holes where the glass fibers literally got pulled out. The two materials just didn't bond together very well, which created all these tiny weak points throughout the whole structure.
Okay, so that's a bit of a setback on the strength front, for sure. But here's the thing about these kinds of scaffolds. Mechanical strength isn't the only thing that matters, not even close. The real test, the life test, is whether it can actually help our bodies grow new tissue.
So let's just reframe the question. Forget about pure strength for a minute. The number one job for this scaffold is to be a welcoming home for new bone cells. So can it do that?
The secret ingredient here is a property called bioactivity. When the researchers put the material with the glass into a fluid that mimics our body, something incredible started to happen. It began to grow this bone-like mineral layer all over its surface. You can see it happening here over 28 days. This layer is basically nature's welcome mat for bone cells.
And here's the big payoff. This data shows that after just 14 days, cell activity on the bioactive glass scaffolds was up to 82% greater than on the plain polymer. So yeah, the mechanically weaker material was actually biologically superior. A huge win.
And the visual proof is just, wow, it's stunning. On day 1, you can see a few lonely cells starting to attach to those bioactive surfaces. But look at day 14. The surfaces are absolutely covered with a thriving network of healthy, happy cells. Now compare that to the pure polymer on the left, it's still pretty barren. It is a total night and day difference.
So, what does this all mean? We have a material that's absolutely fantastic for growing cells, but it needs to be a bit stronger. So what's the path forward to get this from the lab into an actual patient?
Well, the researchers themselves point the way forward. They conclude, and I'm quoting directly here, better mechanical properties may be achieved by improving 3D printed interfaces and the compatibilization between polymer and bioactive glass. In other words, the next big step is figuring out how to make these two materials stick together better.
This whole line of research leaves us with a really provocative thought. Instead of just holding bones together and waiting for them to heal on their own, we are getting so close to building active structures that regenerate them from within.
It makes you wonder, could the future of healing broken bones truly happen from the inside out?